Hey everybody, it's Miss Fiesel here, and we are going to try to take some video notes. Figured it'd be a good time to practice this. Who knows what the rest of the school year will look like. Bear with me though, this is my first time ever making notes like this, so I am going to get your feedback when I see you on Thursday. So these notes we're going to take on a line sheet of paper. So we'll be writing down what I have on the video, just like you would if I was up in the front giving you notes. And in order to make this a little bit easier for you to read, also so that this doesn't take forever here, just on my handwriting part, since I'm trying to do this on an iPad, I will have fill in the blank stuff for me, but any words that are written down as the slides go on, those are all words that you should have on your paper. So I'll give you reminders and time to write, hopefully a sufficient amount of time before moving forward, but we can always pause the video if needed. Sorry, this is going to be very dry, and hopefully in the future I can make this a little more engaging as I get to know the program a bit better. So you should have a line sheet of paper out right now, and we're going to give these notes a title before moving forward, just like we've done our other notes. And we're going to title this Vector Notes. So Vector Notes. These notes will also be posted on Google Classroom if you've missed anything or if you'd like to listen to something again. Alright, so in our everyday world, we run into a lot of numbers all the time. So these numbers represent a certain quantity, and they're given a unit. Generally, there's a unit associated with the number to give that number a specific meaning. Now, we kind of have two categories in which we can classify numerical quantities based on how they are presented to us. The first category is what we call a scalar quantity. So that's what I'm going to fill this first blank with, is a scalar quantity. Oops, there you go. And a scalar quantity is one that has only magnitude. And magnitude is a fancy term for basically just saying there's an amount with it. So even though I've written down scalar quantity, I do also want you to write down this has only magnitude. So if you haven't written that down yet, I'll give you a second. So write out on your paper that a scalar quantity has only magnitude. And again, magnitude is another term for just saying like an amount. So for example, if I said 32 seconds, that would be a scalar quantity. I only have a number, an amount of seconds, 32, and that's it. Or if I said 30 degrees Fahrenheit, again, 30 degrees, I just have an amount and then a unit associated with it just so I know what that number means. A vector quantity, or what makes something a vector, so a vector quantity is one that has magnitude, so there's an amount with it as well, and direction. So this is a quantity that also has a direction that's associated with it. So make sure you're writing down vector quantity has magnitude, amount, and direction. So an example of a vector quantity would be, let's say I was talking about how far something went. I could say 60 meters east. Other directions could be used, like left or right. So force is a vector quantity. We'll talk about forces later on in the year. But if I want to show how much force and in which direction, I could specify the amount of force. Newtons happens to be the unit of force. And say which direction that force was applied. So a vector quantity has both a magnitude, so an amount, as well as a direction associated with it, whereas a scalar quantity just has the amount and that's it. Direction does not matter. Okay, so we have a little bit to write here, so I'm going to kind of give everyone a second to get these couple sentences written down before moving forward, and can always pause the video if I move too fast. But we're going to now look at in what ways we can use vectors and how we can use them. So vector arrows, so we can kind of give vector quantities a picture to give them a little more meaning, to visualize them. And we can do this by using an arrow image. So vector arrows are something that we can use to represent magnitude and direction. A vector is different from another vector if it varies in one of these qualities. So if I'm comparing one vector to another, a vector is only the same if it is the same magnitude and in the same direction. If they vary in magnitude or they vary in direction, then they are considered a different vector. So vector arrows can be used to represent magnitude and direction. A vector is different from another if it varies in one of these qualities. Now we are going to be using vectors right now to represent how far something has traveled and kind of what the journey looked like as it moved. Because we're going to start this quarter looking at different forms of motion and different representations of motion. But again, we'll see these later when we talk about force and momentum, so we can see what direction forces are applied, and we can see how something moves based on its momentum and in which direction. So these vector arrows look like any other arrow. And again, if we're trying to compare magnitude or direction of vectors, let's say I have one vector arrow that is representing 3 meters east. And another representing 2 meters east. Even though these arrows are both in the eastward direction, and we're assuming our north, east, south, west coordinates. So on your paper, it would be similar to kind of what you would see on like a map. North always at the top, east to the right, south to the bottom, west to the left. So if I had one vector representing 3 meters east, another representing 2 meters east, these two are considered different vectors because they vary in magnitude. So even though they are both in the eastward direction, they are considered different from each other because they have a different magnitude. Notice too that this one I drew smaller than the 3 meters east vector. So that was intentional. So we always want to try to, if we can, draw our vectors to scale. If we don't have a scale, then we want to just visually, if a vector is smaller in magnitude than another vector, have it noticeably smaller. See another example. Let's say I have one that is representing 2 meters east. And I have another that's 2 meters north. So again, even though they both are representing 2 meters, these are different from each other. Come on. Well, DIF, that's for different. You get the hint. So these are different from each other because they're in different directions. So one vector is only similar to another if it is the same magnitude and the same direction. So these two are the same. Okay, so next thing to write on our paper, and I'll give everybody a second to do that. Vectors can be positive or negative based on direction. So vectors can be positive or negative based on direction. So they have magnitude, an amount, they have direction, and depending on what direction they are in, they could also represent a positive or a negative quantity. So again, unless you are told otherwise, kind of our golden rule when it comes to directions on our paper that we're working with. North is always towards the top. East is to the right. South is towards the bottom. And then west is on the left. So certain directions are given positive values and certain directions are given negative values. So those that are positive are north, east, up, right, so any type of description that would imply the direction of moving upwards on your paper, or even, I guess, real life, or in the eastward direction. Those that are negative are south, west, down, and left. So southwest, down, and left. And I kind of forgot to put a little up here. So a little plus for positive, minus for negative, or of course you could write out, you know, positive and negative. So kind of where we're getting this from, or maybe where you've seen these directions being positive or negative before, math class, where we have our coordinate planes, we got our x and y axes, this way and this way are positive, so that would be like our northeast, up to the right, and this way and that way are negative. For those of you that have done any coordinate plane work in your math classes. So just somewhere where you might have seen or used these positive directions before. Okay, so where these positive and negative directions will come in handy is when we do a task called vector addition. Vector addition. So that's when two or more vectors can be added together to find the resultant. Two or more vectors can be added together to find the resultant, also known as the sum. So I'll give everybody a second to write that down. So when we have multiple vectors, we can add them up to find what the total value is. So we'll be using this for like journeys or paths taken. So something's moving. Right now we're just going to look at one-dimensional motion, so just going up and down or just going east and west. In the future, we'll be looking at what happens if it goes north and then it turns east for a little bit. But right now we're just going to be looking at one-dimensional straight line motion. But we'll be using vector addition to figure out where something ended its journey. So it starts in a position, it travels, it moves around, it's going to end somewhere. So how far did it go and in which direction is it once it finally ended its journey? So that's how we'll be using vector addition now. We'll also use it though in the future for like forces to find net force. So you have forces applied in different directions. Which way would be the net force? So which way would something move based on the position of all of the forces that are being applied to it? All right, so with vector addition, we're going to take into consideration the magnitude, of course, and then the direction. And so if something is moving in a negative direction, I'll be treating it as a negative number. So let's say I have a small bug that's moving around on my paper, and I mark a starting point, and I want to see where does the bug end up from the starting point and in which direction. So let's say I'm watching the bug and I notice that the bug goes 2 meters north, and then it turns around and it goes 3 meters south. So I'm going to treat that as a negative number. So 3 meters south. And then let's say it turns around and then it goes 5 meters north. Keep that positive because north is a positive direction. And then let's say it decides it's going to turn around again. It's going to go south now. So I have all these vector quantities with different magnitudes and directions, and I can add them up together to find the resultant or the sum. So how far away it is from its starting point, and also what direction, based on if my number is positive or negative. So 2 plus a negative 3 plus 5 plus a negative 2 leaves me with a positive 2 left over. So that means my bug stopped 2 meters north from its starting point. Now, the nice thing about vector addition is, like regular addition, it doesn't matter the order in which you add these numbers. Your resultant, your sum, your answer is going to be the same. So if I did 2 plus 5 in my calculator, I'd get the same answer as if I did 5 plus 2. So the order doesn't matter. All of the opposite directions are going to cancel out, and you'll be left with the same sum. So I could take these 4 vectors and change the order, and I'll still have the same answer in the end. So I could take 5 meters north, and then a negative 2 meters south, then a negative 3 meters south, and then go 2 meters north. 5 plus a negative 2 plus a negative 3, so negative 5, so that's going to cancel. And then plus 2 leaves me with 2 meters north at the end. So order doesn't matter in which you add up your vectors. The biggest thing is just keeping track of positives and negatives based on directions. So let's do a quick little practice problem on your own here. Let's say now I have, oops, to make this a little darker. Let's say I have my bug now, and my bug is now traveling 5 meters east, and then goes, oops, negative 5 meters west. Okay. And then continues to go west. So take a second to do this in your head, or if you want a calculator, got a calculator by you, that's fine. But 5 meters east plus negative 5 west plus a negative 3 west. So that 5 plus negative 5 is going to cancel out. So we're going to be left with negative 3. So that's a negative. So that means we're in the westward direction. If I had a positive 3 at the end, then it would be east, the positive direction. All right, so almost done here. 2 more slides. I'm sure these have been thrilling. All right, so we can use vector addition to solve story problems. So even though I didn't really quite write out a story for you, I just verbally said it, we can use it to solve story problems about motion. We have another method that we can use, though, with vectors to visualize motion. And this method is called the tip to tail method. The tip to tail method. So I'll give everyone a minute to write down the rest of this, the definition of tip to tail method. So when using vectors as a visual, or to find the resultant, so this is another way to, in this case, to visually solve for a sum instead of kind of mathematically find a sum. You draw the tip of the first vector to the tail of the next. They are also drawn to scale if you can. Obviously, we don't have a scale here on our paper, so we're just going to make sure that the ones that are bigger are drawn larger than the ones that are supposed to be smaller. But tip to tail method, when using vectors as a visual or to find the resultant, you draw the tip of the first vector to the tail of the next. They are also drawn to scale. So what we mean by that, what that looks like. So let's say I have a quick journey that I'm taking, and I'm going to squeeze it before this here. So let's say I want to give somebody a visual of something going 5 meters east and 1 meter north. Okay. So I can draw a vector arrow to represent 5 meters east. So I can draw an arrow that's pointed to the right, and I'm going to give that an arrowhead. Okay? I'm drawing the 5 meters east first because that's where we start in the story. So something is starting over here. It's going 5 meters east. It's a bad 5, sorry about that. And then it's going to turn and go 1 meter north. So when you're adding vectors together, we connect them tip to tail. So it starts here, goes 5 meters east, and then if it turns and goes 1 meter north, I'm going to connect the tail of the next vector to the arrow point, the arrowhead of the first one. So that shows I went east first, and then I stopped and went north. So the tip to tail method, the tip of the first vector is connected to the tail of the second vector. Okay, so another helpful thing with vectors, as we started doing with the tip to tail method section, is it can give us a visual too. So not only can we mathematically solve for a resultant sum, so how far something went and in which direction, but we can also visually solve for it using the tip to tail method. And there's a couple of things that we can find using the tip to tail method that we can also solve with vector addition. And again, we're thinking of motion and how something is moving and in which direction and where did it end up once it stopped. So there's a couple of things that we can find. First is the distance traveled. Oops, there we go. Turn the pen on, that'll work. Distance traveled. And so distance is basically the entire path you've taken. So you've started somewhere, you've ended somewhere, so distance takes into consideration every twist and turn you travel. Distance is a scalar quantity. So direction does not matter, and we do not use positive, negative directions when we're solving for distance. We treat them all as positive numbers. So if I start at the high school and I run to downtown and then I decide I'm going to come back to the high school, I'm going to add up the entire length of my journey. Displacement is a term that describes how far you are from your starting point. Displacement is a vector quantity. So when I'm solving for displacement, direction does matter, and negative directions, negative values come into play. Sometimes my distance is the same as my displacement, and sometimes my distance is different from my displacement. And generally, Your displacement is only the same as your distance traveled, if you've traveled in a straight line. So we're going to do a couple examples here just so we can visualize how these two terms are different. And when we're doing vector addition with positive, negative directions, we're trying to figure out where did I end up in which direction. Those previous problems we were doing, we were solving for displacement. I just wasn't quite yet using that vocab term yet. But our tip-to-tail method is going to make these two terms a little bit easier to visualize. So let's say I going to go on a little walk. So I have my little starting point here. And let's say I went 5 meters east. And then I'm going to connect this tip to tail. So make sure you're doing that on your drawing as well. And then let's say I went down 2 meters. And then I went over to the right 2 meters. Ideally, that should probably be a little smaller, huh? So we're trying to keep it to scale. And 2 meters north. And then I went 3 meters. And then I stopped. And I want to figure out the distance and displacement. Okay. So distance. So distance is taking into consideration every single twist and turn of your journey. They're all positive numbers, so we're just going to add everything up. So I went 5 first, then plus a 2, then I did 2, and then I went another 2 meters, then I went 3 meters. So my distance traveled is 14 meters. Displacement is how far I am from my starting point. So I started here and I ended here. So my displacement is that straight line path from where I started to where I've stopped. And again, vector addition can come into play here as well. So kind of what I'm doing is bringing up this 2 to figuring out how long is that straight line path. So that straight line path would be 5 plus 2 plus 3, or 10 meters. I could also solve this using vector addition by adding up all my vectors, and I would see that my positive and negative directions, these guys would cancel. So this -2 would cancel out this +2, and I would end up just with a +5 plus a +2 plus a +3, which would give me 10 meters. So 5 plus -2 plus a +2 plus a +2 plus a +3 would give me 10. So that's another way of solving this problem. Let's do one more. Switch over to red again. Okay, so let's say we'll draw it over. I'm going to draw this over on the right where I have a little more space, and we'll do the distance and displacement on the left here. So let's say I start here and we go up 2 meters, and then we go to the right 2 meters, then we go down 2 meters, left 2 meters, and then I end up stopping where I started. So I end up stopping where I started. And again, we're looking for distance, and displacement. Sorry about the handwriting. Okay, so distance. I'm adding up every twist and turn. It's all positive. Makes that a 2 there. It's all positive. So 2 plus 2 plus 2 plus 2. How far did I go until I stopped? So I went 8 meters. Just going to add up the entire journey. So my displacement is how far I am from my starting point. So if I stop where I started, in the end I never went anywhere. So in the end, my displacement is 0 meters. Vector addition verifies this with our positive and negative directions. So this positive to north gets canceled out with this negative to south, and this positive to east gets canceled out by this negative to west. You could also just add it up. So 2 plus a negative 2 plus a negative 2, I'm sorry, 2 plus a positive 2 plus a negative 2 plus a negative 2. That would also give me 0. The 2 plus 2 would give me 4, and then the negative 2 would be a negative 4. So I'd end up with a 0 at the end. So distance is how far you've traveled, the entire length of your journey, and then displacement, how far you are from your starting point. So we're going to do a short worksheet here where we're going to practice using these terms and practice drawing some journeys, this time to scale. And I'll have corrections for that as well. These notes will be posted on Classroom, so if you need to see them again later, or if you have headphones, you're going to pull them up again in class, that's fine. But these will be posted, so you have a way to access them in case you've missed anything or you've wanted to hear anything. See you on Thursday. Thanks for being patient and giving these a shot for me, and look forward to hearing from you how this all went. Hopefully it wasn't too crazy. Have a good day, everybody. Bye.